Today we discuss about layout of current mirror and mismatches of current mirror and the techniques to improve the mismatching so that it will be better matched in the current mirror. The two transistors has to be must matched perfectly to get the perfect ratio at the reference current compared to input current. Before going for the layout of simple current mirror, first of all, whenever a transistor is fabricated, the drawn length is going to be different from the effective length of the channel, because normally gate is going to be fabricated and gate is overlapped on source as well as drain like this. So this is DL. DL is nothing but overlapping of gate on drain as well as on source. So normally whatever we take L is equal to, that is nothing but drawn length. Let us assume L is equal to 5 micrometers. That is 5 micrometer is nothing but drawn length. But effective length at the time of fabrication it will be lesser than that one. So L effective is nothing but L drawn minus 2 times of delta L. L drawn minus 2 times of delta L. So, and that too why we have to consider is nothing but whenever we are going for the actual transistor, it won't be exactly like this dimensions. It will be in this manner. This is the actual transistor where the length and width is going to be totally different. So not only for length, it will be always there is a small difference in width, that is effective width is different from drawn width. So generally we can make L effective is equal to L drawn minus delta L, W effective is equal to W drawn minus delta L. So whenever laying out the current mirror, the lateral diffusion and oxide encroachment on the length and width of MOSFETs must be considered. That is, we have to consider this delta L as well as delta W. So we must go with L effective and W effective, not the L drawn and W drawn. This is what the simple current mirror we are discussing about. Simple current mirror consisting of two transistors M1 and M2 perfectly matched with equal W by L ratios, and by that time the reference current is going to be mirrored at output current. I out is equal to I reference, and if widths are going to be different at that time, I out is equal to W by L of 2 divided by W by L of 1 into I reference. So here, if widths are going to be different, you will be getting a ratio of currents, otherwise you will be getting the exact current, that is mirrored current. So while we are going for the laying out of simple current mirror, already we discussed one important point. L is equal to 5 micrometer we are assuming, because even though we are going for 2 micrometer technology, 5 micrometer is nothing but the minimum channel length we are assuming for analog design. Minimum channel length will be considered only for digital designs, whereas minimum channel length will not be considered for analog design. Because if you consider minimum channel length for analog design based on channel length modulation effects, that effect is going to be much more severe when the length is small. So normally the length we will take for analog design is going to be more than the minimum length of technology. And once the length is fixed, it will not be changed. Only we will be getting a change in the width. Width of the MOSFET is going to be changed, but not the length. So I out is equal to W by L of second transistor by W by L of first transistor into I reference current. Whenever we are considering oxide encroachment and lateral diffusion, by that time there is a difference in this ratio of W by L of second transistor to first transistor, that is nothing but W2 L1 by W1 L2. But we know that one lengths of MOSFET are fixed. So here if you take length ratio L1 by L2, that is L1 drawn minus delta L, L2 drawn minus delta L, that is always equal to unity, since lengths once fixed it won't change. So that we no need to bother about L1 by L2 ratio. So what we have to bother is nothing but what happens to W2 by Wn. If there is a error in W2 by W1, at that time there is the error in the output current with respect to reference current. That we will see now. If you want to get multiple currents in the output current mirror, at that time the widths are going to be ratioed accordingly. So the widths of the devices determine the relative currents in the mirror. So widths cannot be equal like lengths. So whenever we are going for more width, at that time we should consider some precaution. So there are two diagrams indicated, A and B. First one is with no width correction, the second one is nothing but mirror with width correction. So both are going to be simple current mirrors only, which will be consisting of M1 and M2, whose sources are tied together, and M1 drain is connecting towards resistor R through VDD, and M2 is connecting towards output side like simple current mirror. So this is without width correction. Let us assume the width of second transistor is 4 times than width of first transistor. That is W2 is equal to 4 times of W1. So M2 transistor width is 4 times of W1, and M2 transistor has taken as a single transistor whose width is 4 times of first transistor. That's why this is first transistor and this is second transistor. This is polysilicon. This one polysilicon, and above that one drain, here also above that one drain, below that one source. So sources are going to be shorted together. This source M1 source and this is M2 source, both are shorted together, and it is given to VSS, and M1 drain is connecting towards R, M2 drain is connecting towards output. For M1, gate and drain are going to be shorted together. So this is gate and drain are going to be shorted together. So this is a simple current mirror without width correction. That is nothing but we have taken M2 transistor as a single transistor. The width is nothing but 4 times of M1 transistor. Now this is with width correction. Width correction, if you cleanly observe, this is there is a lines, different lines you will find. These are the lines. So that implies this is M1 transistor, and replica of M1 transistors has been used 4 times. Assume M1 transistor is a unit transistor, and this M1 transistor has used 4 times to get M2 transistor. So M2 transistor is made up of 4 times 4 unit transistors. This is nothing but width correction. So what happens if without width correction? What happens if width correction? How do we eliminate the error in the ratio? That we will see now. This is one more diagram indicating the same thing. Here you may be getting this clearly. This is a simple current mirror. For that one, without width correction. Without width correction is nothing but this is M2 transistor and it is M1 transistor. Drain and source. This is polysilicon, and this contact is saying that drain and gate are going to be shorted for M1 transistor, and there is no short over here. So M2 transistor is going to be having a length that is equal to 4 times of M1. Without width correction, M2 is a single transistor. Here if you observe, M1 is going to be, this is the transistor, M1 source, M1 source and M2, M1 source and M1 drain, and drain and gate, this is polysilicon acting as gate. So gate and drain are going to be shorted together. This is the contact which shorted gate and drain for M1. And M2, if you observe, it is not a single transistor, it is M2A, M2B, M2C, M24. all 4 transistors are equal to unit size of M1. So now M2 transistor is going to be sum of 4 unit transistor whose length is going to be same as M1 length, but width is 4 times of M1 transistor. This is with width correction. The width ratio is defined W2 by W1 is nothing but W2 drawn minus delta W by W1 drawn minus delta W. If width correction is not taken, at that time the ratio is not equal to integer. If width correction is taken, the ratio is exactly equal to integer. We will see. For example, we are going with no width correction. So W2 is equal to 10 micrometers, W1 is 5 micrometers for example, and the delta W is zero point 0.5 micrometers. Width ratio is nothing but W2 effective by W1 effective. 10 minus zero point 0.5 micrometers divided by 5 minus zero point 0.5 micrometers. So it is 9.5 divided by 4.5, which is not an integer. Whenever we are going with drawn lengths, at that time the ratio is 2, but here the ratio is greater than 2. So it is not an integer. Definitely the expected thing is only twice of the input current. Here it is more than twice of the input current. This is what considered as error, since no width correction has been taken care. Next, with width correction, the layout of M2 is basically 4 MOSFETs in parallel. So width ratio W2 by W1, we can write it as 4 times of W1 by W1, and if you are going with W1 effective, 4 into W1 minus delta W, W1 minus delta W. So here exactly you will get an integer. So if you consider the ratio of widths, if you consider width correction, at that time the ratio is going to be maintained as integer. Otherwise there is a slight difference. So I out doesn't track reference current as expected. Next topic, matching in MOSFET mirrors. Matching in MOSFET mirrors, that is how to match M2 and M1. Those two transistors in the current mirror must be matched perfectly such that I out is going to be equal to I in, otherwise it may be multiple times of input current. So before going for the matching, we will see what are the different effects are there which causes mismatching in MOSFETs. So they are going to be normally considered as first order effects. The first order effects in MOSFET mirrors are going to be, there are three important first order effects we are going with based on the drain current equation. Drain current equation I out is equal to K into W by L into VGS minus VT whole square. If you consider channel length modulation, at that time I is equal to K into W by L into VGS minus VT whole square into 1 plus lambda VDS. From this one, first effect we are considering is threshold voltage mismatch. Even though we are going for the same fabrication, there is a slight change in the threshold voltage. So we are assuming that one only mismatch is occurring in threshold voltage and all other parameters are exactly matched. So this threshold voltage mismatch is distributed across both devices equally such that Vt1 is equal to Vt minus zero point 0.5 delta Vt, Vt2 is equal to Vtn plus zero point 0.5 delta Vtn, where Vtn is the average value of Vt1 plus Vt2 and delta Vt is the mismatch. So here we are assuming that one threshold voltage mismatch is equally distributed towards M1 and M2 transistors, and the maximum mismatch is nothing but delta Vt. By assuming perfect matching of all other parameters, the ratio of currents I0 by I1, we can write beta into VGS minus VT2 whole square, beta into VGS minus VT1 whole square. Only the threshold voltages are taken different, VT2, VT1. I naught by ID1, which is equal to VT2, and VT1 has substituted, and after simplification and higher order terms are ignored, at that time I naught by ID1 is approximately equal to 1 minus 2 times of delta VTN by VGS minus VT. This is the ratio of output current to input current in case of simple current mirror when threshold voltage mismatch is considered. When threshold voltage mismatch is considered, as VGS decreases, this term increases. So this term increasing is nothing but ratio is going to be less than 1. So the difference in the current mirrors increases because of threshold voltage mismatch. So for large VGS the effect is small, for small VGS the effect is large. Second mismatch in transconductance, and that too the transconductance we are preferring is process transconductance indicated with K. Beta is also considered as transconductance, but that is called as device transconductance. K is called as process transconductance because the value of K totally depends on process. It is not in the hands of designer. K is equal to mu into COX. Mu is nothing but mobility of charge carriers. COX is nothing but oxide capacitance. Both are not at the designer's hand. Designer cannot change these parameters once that process technology has been adopted. So that's why K is called as process transconductance, whose value is fixed for the given technology. Whereas beta is device transconductance, the value is K into W by L. K is fixed, but W and L are going to be width and length ratios, which are in the designer hands. So designer can vary width as well as length, so that beta can be varied. So beta is called as device transconductance, K is called as process transconductance. Okay, assume that mismatch in transconductance is distributed across both devices such that Kn1 is equal to Kn minus 0.5 delta K and Kn2 is Kn plus zero point 0.5 delta K. Again we are assuming that the mismatch is equally distributed across both transistors, where Kn is the average of Kn1 and Kn2. Assume perfect matching on all other parameters of drain currents, so that I0 by I1 is simply equal to Kn2 by Kn1, that is Kn plus zero point 0.5 delta and Kn minus zero point 0.5 delta, which is approximately equal to 1 plus delta K by K. So as the mismatch is going to be increases, at that time the ratio is going to be gets differed by a large amount. Now the third one, in the same manner, if mismatch in lambda VDS product, the product of lambda and VDS, this is also gets mismatch while fabrication. So in the same way, if you assume only this parameter is going to be gets affected and all others are going to be perfectly matched, at that time finally the ratio of output current is yielding like this: 1 plus lambda 2 into VDS2 divided by 1 plus lambda 1 VDS1. Normally lambda into VDS product, out of that one we cannot change the value of lambda, only the thing is VDS value can be obtained. So if possible, effort should be made to design the circuit such that the values of VDS must be equal. In the circuit VDS1 is equal to VDS2, we can make that one, but we cannot change lambda 1 and lambda 2. So as we have done in cascode current mirror, VDS1 is equal to VDS2. In that way we can achieve VDS1 and VDS2 are equal values, but there is no chance of getting lambda 1 and lambda 2 equal. Next, layout techniques to improve matching. This is the first layout technique. We know that one minimum size devices are rarely used in analog applications, but the larger devices can result in larger parasitics if some layout issues are not considered. For analog design, we don't go for the minimum size length transistors, so always it is going to be more than minimum size as length of channel. So this is, and large length implies nothing but the width has to be very large, because W by L is going to be the basic transistor, and whenever we are going to increase the output reference current, at that time W is going to be multiples of current. So length is large, W is large, and W is going to be multiplied by some integer is nothing but that is very very large. So for example, consider this A, large device with a single contact. Large device with a single contact, that contact is made like this is a single contact on drain and on source. So and others is nothing but there is no other contact, one side is source, the other side is drain. This black is nothing but polysilicon. By that time simply source and drain are going to be n plus diffusions. In case of npn transistors, n plus diffusion is going to be considered as a distributed resistor. So if there is no contacts except for this single contact, by that time this entire area is going to be act as a distributed resistance which is going to be adding. So a large resistance value across n plus source and across n plus drain results, that is nothing but unwanted, so which slows down the transistor operation. So the equivalent value is going to be given like this. It will be assumed as a large transistor whose resistance across source and drain is going to be very large. How to reduce this one? The diffusion resistance can easily be reduced by simply adding as many contacts as possible along the width of both source and drain. Look at this third one. This is, previously there is only one contact, now we have made the maximum number of contacts which are possible on source as well as drain. Contacts are normally either may be connected towards VDD or VSS depending on the N or P region. So by that time they are going to be connecting towards ground in terms of AC analysis. So the resistance is going to be minimized. If you increase number of contacts at that time, the distributed resistance is going to reduces, and current capability is going to be increases since resistance is reduces, and more distributed current throughout the device. You are going to be getting equal current throughout the device because of these contacts. Otherwise there is a slight change in the current at contact area and at some other places. So the increase in number of contacts results in lower resistance, more current capability, and more distributed current load throughout the device. This is the first technique to improve layout. Second technique to improve matching is inserting dummy poles. Inserting dummy poles and taking the width of larger transistor as multiples of unit transistor. So that don't go for a larger width transistor as a single transistor. So larger transistors always should be modeled as a parallel combination of unit transistors. That is the first thing, and for those things we must use dummy polystrips. So this is, assume that one width of m2 is going to be 4 times of unit transistor. So that this is first transistor, second transistor, third transistor, fourth transistor. These two are going to be polystrips which are going to be considered as extra polystrips. Even if you remove these two things also, it will be considered as a width of 4 times the basic cell. But these are going to be treated as dummy polystrips. If they insert it, that will be having an advantage. Otherwise there is no change in the operation except small errors.